An experimental activation involving a spherical device was followed by the emergence of a field so intense that the entire facility had to be cleared. Researchers at MIT carried out what has since been referred to as the bugosphere test. The system was reportedly intended to investigate exotic energy configurations, potentially attempting to tap into quantum vacuum fluctuations. Something, however, failed in a catastrophic and uncontrolled way. The field could not be contained. Emergency procedures were triggered. MIT police were contacted. Everyone was ordered to leave immediately. This was not a chemical leak. It was not a fire. At an institution accustomed to handling dangerous substances and extreme high-voltage systems. An evacuation order only comes when the risk is immediate, widespread, and potentially fatal. What has not been openly discussed is that only a few scenarios could justify a response of this magnitude. One possibility is a magnetic hyperquench releasing gigajoules of stored energy. Another is a quantum vacuum instability, generating non-thermal fields capable of disrupting biological systems. A third involves localized distortions of space-time, producing gravimetric pulses. Each scenario implies physics operating at the absolute boundary of what humans can currently control. The so-called bugosphere model itself is revealing. The terminology implies a spherical geometry designed to probe highly esoteric physical regimes. Related theoretical concepts describe a device that could allegedly absorb around 100 watts of energy continuously from its surroundings without any visible input or loss. Such a claim directly challenges established thermodynamic principles. If any form of non-conservation were physically real, the mechanism would have to draw from the zero-point energy field, the minimum energy state inherent to quantum systems that never truly becomes still. Some theories suggest this energy could be accessed under very specific conditions. In these models, spherical symmetry is not a design choice, but a requirement, particularly when defining strict geometric boundaries for manipulating quantum fields. The sphere is essential for controlling boundary conditions and stabilizing quantum vacuum fluctuations. The most conservative scientific interpretation points toward research connected to the Casimir effect, the force that arises between macroscopic objects due to altered vacuum energy densities in quantum electromagnetic fields. Precision experiments that measure Casimir forces typically rely on spherical or parallel plate geometries. If the experiment involved a tunable spherical resonator, perhaps concentric shells or a single shell interacting with an external boundary, the goal may have been to dramatically shift local energy density differentials. A design error or material failure in such a system could, at least in theory, result in a sudden and measurable net energy release. This leads to the proposed containment failure mechanism, a rapid, uncontrolled instability in the geometry of Casimir structures could produce an instantaneous release of vacuum energy. Such a release would not behave like heat or conventional radiation. Instead, it would manifest as a highly localized, high-density energy field from a quantum field theory perspective. The uncontained field could resemble a temporary topological defect, a brief breakdown in the ordered structure of the quantum system. If the sphere was intended to induce exotic phase transitions or manipulate space-time geometry itself, then the failure would involve energy being released through non-electromagnetic channels. Hazards of this nature cannot be managed using standard chemical or radiation safety procedures, which would explain the urgency of a full evacuation driven by the unpredictability of interacting with localized failures of established field theory. One plausible explanation is a magnetic hyperquench. Among non-nuclear mechanisms, the most credible way to generate energy fields severe enough to require immediate evacuation is a catastrophic failure in a high-field magnetic confinement system. MIT's plasma science and fusion research facilities specialize in precisely this kind of technology. The Institute has achieved world record magnetic field strengths, with prototype magnets reaching around 20 Tesla using high-temperature superconductors. Fusion devices rely on these magnets to confine extremely hot plasma, and the energy stored in such superconducting systems can reach from megajoules to gigajoules. The weak point in any superconducting magnet is the quench, a sudden transition from zero electrical resistance to a normal resistive state. When this happens, the stored magnetic energy is converted into heat almost instantaneously. Quenches can be triggered by internal material defects, mechanical movement of wires, cracking in structural resins, failures in control systems, or loss of cryogenic cooling that keeps the system superconducting. In an uncontrolled hyperquench, the rapid energy dump causes extreme thermal and mechanical stress. Even energy releases in the megajoule range are sufficient to melt large amounts of copper. The resulting electromagnetic forces can be violent enough to physically displace metal components. Safety documentation emphasizes this exact danger. The hazardous field that would justify evacuation could result directly from a runaway magnetic collapse. MIT safety standards define a 5 Gauss boundary to protect individuals with medical implants such as pacemakers. In a hyperquench, the sudden collapse and spread of multi-Tesla magnetic fields could push this dangerous boundary far beyond its intended shielding, forcing evacuation of not just a single room, but an entire building and nearby structures. The urgency arises from multiple threats. There is the immediate risk of flying debris caused by extreme electromagnetic forces, as well as the possibility of structural damage to the facility itself. A rapid collapse of high-energy magnetic fields also induces massive eddy currents in surrounding metal through electromagnetic induction. These currents generate severe mechanical stresses in both equipment and building infrastructure. In addition, they can produce powerful electromagnetic pulses similar to those seen during major plasma disruptions in tokamak reactors. Such an EMP could disable electronics or trigger cascading system failures across multiple floors. Evacuation protects against physical destruction, airborne metal fragments, and widespread electronic failure throughout the complex and nearby buildings. A far more speculative explanation involves localized space-time distortion. In this scenario, the field was not electromagnetic at all, but a transient manipulation of the structure of space-time itself. Research tied to advanced propulsion concepts suggests that generating measurable distortions in space-time would require extreme energy densities, approaching those found near black holes or during the earliest moments of the universe. MIT's high-energy density physics research examines matter under similarly extreme conditions. Work in advanced electrodynamics and propulsion theory explores whether localized gravitational effects could be produced, sometimes using high-voltage systems such as spark gaps to momentarily achieve immense energy densities. If such an effect were ever confirmed, it would represent a profound shift in our understanding of propulsion and energy control. Highly speculative experiments tied to ideas such as the Alcubierre warp drive depend on extremely isolated laboratory environments and advanced optical measurement techniques. Interferometry is typically used to detect incredibly small changes in optical path length that would indicate spatial distortion. If the bugosphere experiment succeeded in generating localized space-time distortions using exotic matter analogs or extreme energy gradients and then lost containment, the resulting field effects would be profoundly unconventional. The signature of such a field would be gravimetric rather than electromagnetic. Standard instruments designed to detect radiation or magnetic fields might register little or nothing, complicating any immediate emergency assessment. The earliest observable signs could be unexplained fringe shifts in laser interferometers or sudden, anomalous physical forces acting on nearby test equipment. An uncontrolled collapse of a distortion field could release stored potential energy in unusual forms, possibly generating short-lived gravitational wavelet pulses. These could manifest as non-directional acoustic shock waves or intense structural resonances propagating throughout the building. The evacuation trigger in such a scenario would be rooted in absolute uncertainty. If the field involved localized manipulation of space-time itself, evacuation would be justified by the complete unpredictability and unknown biological risks associated with exposure to altered geometry. Fields capable of modifying local gravitational potential or time dilation have never been studied from a physiological standpoint. Potential biological consequences could range from immediate disorientation to non-thermal cellular damage or sudden internal pressure imbalances. A critical failure would likely arise from errors in generating or stabilizing highly complex field structures. This could involve systems conceptually similar to gravitational wavelet phased arrays, designed to produce constructive interference in gravitational effects within a confined volume. If synchronization failed, interference patterns intended to remain inside the spherical apparatus could abruptly shift outward, releasing powerful, uncontrolled pulses of gravitational energy into the surrounding structure. Such an event would demand immediate evacuation due to the risk of structural compromise and disruption comparable to seismic activity. entirely separate from fire or electrical hazards. At institutions like MIT, which routinely manage cutting-edge and high-risk research, emergency response follows strict, layered preparedness protocols covering chemical, radiological, and mechanical incidents. Failures involving high fields or exotic phenomena bypass these standard categories instantly, escalating a laboratory anomaly into a life-threatening emergency. In such cases, direct involvement of campus police becomes mandatory when a field cannot be clearly identified as chemical, thermal, or radiological. Safety doctrine requires assuming the highest risk scenario. This almost always involves uncontained high-field magnetic or unknown force events, which necessitate establishing large safety perimeters. These perimeters are designed to protect individuals with medical implants by clearing areas far beyond theoretical 5 Gauss safety boundaries. The evacuation itself is not discretionary, but a direct consequence of safety regulations governing extreme, uncontained field events. The impact on infrastructure extends well beyond the experimental chamber. High-energy research environments frequently operate above 50 volts and often exceed 600 volts, levels that already require explicit high-voltage warnings. Field failures that produce intense electromagnetic spikes can trigger massive electrical arcing. In fusion-related settings, such surges can transform diffuse arcs into tightly constricted plasma columns, rapidly eroding components and destroying equipment. Modern research facilities are densely packed with precision electronics, sensitive optical tables, ultra-fast laser systems, and high-resolution spectrometers. Sudden bursts of magnetic energy or even more exotic gravitational disturbances could cause non-thermal interference, injecting noise, corrupting data, or disabling entire computing systems across multiple laboratories. One particularly serious but often overlooked vulnerability is proximity to advanced computing research. If the incident occurred near laboratories working on quantum computing or highly sensitive materials science, transient exotic fields, especially those involving topological phases or symmetry breaking in quantum systems, could cause immediate decoherence or irreversible data loss in nearby hardware. This represents a high-value failure mode independent of visible physical damage and would justify the heightened security and secrecy that often surround such incidents. The question of biological risk further complicates the situation. Public health authorities generally agree that existing evidence does not demonstrate clear links between ordinary electromagnetic field exposure and harmful health effects. However, the nature of the bugosphere field demands consideration of non-standard outcomes. If the field originated from quantum vacuum phenomena or exotic energy sources, it could produce non-thermal high-energy radiation through particle interactions, such as Compton upscattering leading to localized gamma emissions. Evacuation serves as protection against unknown exposure thresholds associated with unconventional radiation profiles. If the field emerged from vacuum fluctuations, it would still obey Lorentz invariance and not violate special relativity. Yet its interaction with complex biological tissue or sensitive electronic medical implants remains largely unexplored territory in advanced physics. The evacuation procedure therefore functions as a universal protective response, effectively extending the 5 Gauss safety principle to any high-magnitude, uncharacterized force field. When the nature of the hazard is unknown, worst-case assumptions are mandatory, and the safest option is to clear everyone from the area. This uncertainty is what makes such scenarios especially dangerous. Standard safety protocols are built on decades of research into how known hazards affect the human body, defining chemical exposure limits, radiation dose thresholds, and electromagnetic field tolerances. When an experiment produces a field that fits none of these established categories, something that may be drawing energy from the quantum vacuum or altering local space-time, there is no biological data, no exposure studies, no safety margins, and no medical response framework. That absence of knowledge alone justifies immediate evacuation, because the consequences of misjudgment in such a situation would be catastrophic and irreversible. The broader implications are strategic in nature, regardless of the exact failure mechanism. The capabilities implied by the bugosphere experiment carry serious consequences for future technology development and national security planning. If the bugosphere truly represented an advanced energy system capable of tapping zero-point energy or enabling practical fusion-based power, then successful containment would fundamentally transform the global energy landscape. It would make carbon-free power generation possible at scales far beyond what exists today. At the same time, the incident highlights the existential risks involved in scaling and containing power sources that fall outside conventional physics. The long-term objectives of this kind of research often align closely with defense priorities. Compact, high-output energy systems are essential for emerging military technologies, including mobile microgrids that reduce reliance on vulnerable fuel supply chains. Beyond energy, any verified ability to generate localized space-time distortions or anti-gravitational effects would immediately open the door to revolutionary propulsion systems. Such breakthroughs could compress interstellar travel times from tens of thousands of years to spans compatible with human lifetimes. That is not speculative fiction. It reflects the stated research motivations driving some of these experiments. The reported evacuation underscores the need to fundamentally rethink containment engineering when dealing with non-classical or extremely dense energy states. Future high-field and high-energy density research facilities must be designed with structural resilience capable of withstanding massive impulse loads, whether from magnetic quench events or potential gravitational anomalies. This means materials and architectures that tolerate not only heat and mechanical stress, but also sudden, nonlinear pressure forces produced by collapsing magnetic fields or distorted space-time geometries. Equally important is the failure of diagnostics. The incident suggests that existing monitoring systems were unable to provide sufficient warning. Experiments involving advanced field manipulation require next-generation multimodal sensor arrays capable of detecting more than standard electromagnetic signals. These systems must be able to register transient gravitational disturbances using ultra-sensitive interferometers and gravimeters, as well as exotic quantum signatures that indicate symmetry breaking or phase transitions. Such diagnostics are essential for triggering automated shutdowns and containment responses far faster than human reaction times allow. When operating at energy densities near theoretical limits, microseconds matter. Human intervention is simply too slow. Automated systems must detect anomalies and act before cascading failure begins. The bugosphere incident implies that current diagnostic capabilities are inadequate for the regimes of physics now being explored. Research is pushing into domains where sensors cannot fully characterize events quickly enough to prevent accidents. The scale of the institutional response, a full building evacuation, suggests the field was either electromagnetically extreme or fundamentally non-conventional and biologically unsafe. Typical electrical, fire, or chemical emergencies are handled with localized containment. A pervasive, unidentified field indicates a hazard that exceeded known mitigation strategies or posed unknown biological risks. In such cases, the only responsible response to a macroscopic, uncharacterized field, especially one that may challenge established physical limits, is immediate. Large-scale evacuation. That classification elevates the incident to a top tier. Life-threatening emergency. The spherical design of the apparatus further implies optimization for complex field confinement. Whether intended for uniform energy distribution in high-energy density experiments or precise tuning of quantum boundary conditions in Casimir-type systems, the failure likely involved a catastrophic structural deformation or synchronization breakdown that instantly released massive stored energy or field potential. Three explanations remain plausible. One is a magnetic hyperquench caused by superconducting failure, which is particularly credible given MIT's fusion research background. Another is quantum vacuum instability, destabilizing Casimir cavity structures and producing exotic energy leakage. The third involves localized space-time distortion arising from ultra-high energy density systems, generating gravimetric anomalies. Each scenario explains why standard safety protocols were insufficient. Each necessitates evacuation because conventional protections do not apply when experiments manipulate fundamental fields or space-time geometry itself. The incident serves as a potential case study demonstrating the urgent need for investment in next-generation containment systems and diagnostics. Experimental physics is approaching an era where laboratory conditions resemble those found only in stellar interiors or near black holes. Existing facilities were never designed for that reality. Safety protocols evolved around familiar hazards, and diagnostic tools are not equipped to fully characterize exotic fields in real time. If the bugosphere incident occurred as described, it exposes the gap between scientific ambition and engineering capability. Humanity can create these extreme states, but cannot yet reliably control them when something goes wrong. That gap represents a serious risk not only to researchers and facilities, but potentially to surrounding communities if failures propagate beyond a single building. The physics being explored demands engineering solutions that do not yet exist and safety frameworks that have not been fully developed. The field that allegedly forced evacuation, whether magnetic, quantum, or gravitational, exceeded all containment expectations. It became uncontrolled, posed a direct threat to human safety, and required clearing entire structures. Most importantly, researchers were unable to characterize it quickly enough to deploy targeted countermeasures. That is the central lesson. Experimental failure is expected in frontier research. What is alarming is that current infrastructure cannot safely accommodate the physics being pursued. Facilities operating at these limits lack sufficient containment margins and real-time diagnostics. The next incident may not end with evacuation alone. It could result in permanent facility loss or casualties if a field propagates faster than emergency responses can act. Many questions remain unanswered. What was the bugosphere actually designed to achieve? Was it focused on vacuum energy extraction, space-time manipulation, or advanced fusion confinement? No official clarification has been released. What specific measurements triggered the evacuation? Was it magnetic field strength surpassing 5 Gauss safety boundaries, unexplained forces detected by interferometers, or structural stress readings indicating imminent failure? How long did the uncontained field persist? Minutes, hours, or longer? Did it decay naturally, or was it suppressed by emergency shutdown procedures? What damage occurred to the facility and equipment? Was the apparatus destroyed? Did nearby experiments or infrastructure suffer permanent harm? The absence of answers is itself telling. When cutting-edge physics experiments fail catastrophically, institutions often limit public disclosure to avoid regulatory scrutiny that could restrict future research. The bugosphere test represents physics at the outermost edge of human capability, where theory confronts experiment, containment engineering meets barely understood forces, and safety protocols designed for conventional hazards fall short in the face of exotic phenomena. The experiment illustrates what happens when ambition outpaces infrastructure. Another test is likely already being prepared somewhere, another sphere, another attempt to harness fundamental forces. Now there is precedent for what can happen when containment fails. Whether that precedent leads to meaningful change remains an open question.